Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, shortest subarray to be removed to make array sorted. I feel like this is an interesting problem because honestly, conceptually, it's not that complicated. It's pretty easy to figure out generally how you want to solve the problem, but then actually dealing with like all of the edge cases is really annoying and just kind of tricky, I guess. Once you see the solution, it works, it makes sense, and it's very simple. But actually arriving at the solution is difficult, so we'll definitely be focusing on the conceptual parts. The idea is pretty simple. We're given an integer array of positive values. Well, I guess they could also be 0, but it's not really relevant to this problem. We want to remove a subarray from here such that the remaining elements in the array are non-decreasing. So basically that they're in increasing order, but we could also have a tie. So something like 1, 2, maybe another 2, and then a 3. So what's the smallest subarray we could remove from this array to make it sorted? Well, it's already sorted, so we remove nothing. Now, you might be thinking that, is the problem description too short? What if we can't find a subarray to remove? Well, how could that possibly be the case? Because if you just have a single value, well, that's definitely sorted. So we could just take the first value and then remove everything else. So there's definitely going to be a solution. Either we remove an empty subarray of size 0, or we remove n minus 1 elements. The result should never be larger than this. So how do we do it? Well, sure, we could probably arrive at a brute force solution that's of n squared. Even that probably wouldn't be trivial. I'm not even sure if it's necessarily possible the way I'm thinking of doing it, because we know that there's going to be roughly n squared subarrays. So you could try something like this. Okay, try removing this subarray. Is everything else going to be sorted then? Like basically we're trying to find the shortest subarray starting at every element. But for us to do that, then we have to kind of go through the rest of the array. There might be a way to do it. Maybe some kind of way, like if you have all the postfixes of the array, and then for each postfix, you could maintain like the max element, or rather the minimum element, because we want to ensure that everything that came to the left of it is less than or equal to the minimum element on the right side. But I won't go too further in this explanation because I haven't really thought too much about it. Even just thinking about it, you realize that, okay, it's not going to be a trivial way to do it. So how can we arrive at a better solution? Let's think about it. Let's say I have an array that looks like this one. Let me visualize it. Not the best drawing, but I hope this gives a little bit of the intuition. When you look at a picture, it becomes kind of obvious. If we just remove this, then everything is in non-decreasing order. We have a tie among these elements, but that's not a problem. When you have two adjacent elements, such as these ones, that are in decreasing order, it's pretty much guaranteed that one of them has to go. There's really no other choice. Either this guy has to go or this guy has to go. So let's think about how to do this. By looking at this example and a few of the examples that they actually gave us in this problem, I think it's not super crazy to arrive at a solution like this one where you recognize that, okay, let's just scan left to right. Let's say, okay, this is an increasing order, this is an increasing order, this is an increasing order, that's good. This is also an increasing order, but this is not. So now I have multiple choices. I could say, oh, well, this is not in increasing order. I mean, it's possible that we could just remove a single element, who knows? But at this point, I know at the very least, all of these guys were in non-decreasing order. So I could say, remove this postfix. Everything after that, I can guarantee that this is the longest prefix that is in increasing order. So this is one possibility. I don't necessarily know that this is the minimum subarray that we could remove, but this is the minimum postfix that we could remove. When you realize that, it becomes kind of clear that, okay, well, if we're going to remove the minimum postfix, we should also try to remove the minimum prefix, and it's going to go in reverse order. So you start all the way at the right. We say, okay, these two are in non-decreasing order. That's good. So we shift the pointer, we're looking here, compare these two, it's good. We know like all of this is in non-decreasing order at this point, and then we'll compare it over there, and we'll see that, okay, these two are not, like this is bad, so we can't really go any further. But we know that all of these are in non-decreasing order, so this is the shortest prefix that we could possibly remove. And so the length of this subarray is 4. The other one that we saw, the postfix, the length of that was 3. So among those two, the minimum is 3. So is that the solution to the problem? No, because there are really three cases. Either we remove a prefix from the array, or we remove a postfix from the array. Like the minimum subarray we could remove is a postfix or a prefix, or the third case, which is, in this example, a subarray in the middle. And in this case, it's just of length 1. So that is the solution in this case, and that's the difficult part. It's not hard to code up a solution that satisfies these two, but handling that third case, when there is an example that requires us to remove from the middle, that's going to be difficult because the examples could be different than what I've shown you. This example makes it seem like it's going to be trivial. It makes it seem like you could have a two-pointer approach, just starting this here and this over here. And, while this is like less than or equal to each other, we can keep shifting the pointers, but that's not actually going to be possible in this problem for multiple reasons. And I'll kind of show you an example of where that would happen. Let's consider this example where now the shortest array for us to remove is actually this one here. It's of length 2. Now, by looking at this, you might think, well, the pattern must be that if there is a middle array, the one that we should remove is always going to be in decreasing order, or maybe these could have been like the same element 10. But at the very least, it's obvious by looking at this, we can only keep one of these. We can't keep both of these because for all these elements, we need to make sure that everything to the left is less than or equal to 6. For all the elements over here, we need to guarantee that everything is greater than or equal to 9. So clearly there's a contradiction. Either remove these two or remove these three. But the difficulty comes from identifying this because, like I said, this could have been different. I could have actually put an 11 over here, and this still would have been the subarray that we want to remove. So how do we identify the middle one? My first attempt was actually to try a two-pointer approach, having a left and right all the way at the ends of the input, because we already discussed that the prefix and postfix are pretty easy to identify. And it kind of works for this example because what we're saying is if this value is less than or equal to the value over here, then at the very least, we know that everything like up until this point is less than or equal to everything up until this point, and thus this is the middle array for us to remove. And then we will try to shift our pointers inward. The problem is we don't really know how to shift the pointers, and there are multiple reasons for that. The fact that we could have ties, like we could have adjacent elements that are equal. Suppose we had like a 7 over here. We don't necessarily know which pointer do we want to shift. Well, to this 7 or to that 7. In this case, it might not matter, but then we look at like the following elements. It can get more complicated. Even more so if I were to take this part and also replace it with like a 1, 2, 3. We can tell right now that by looking at it, either we remove all of these or we remove this part. In both cases, the subarray that we remove is of length 5, but again, you can imagine I could have changed this. I could have put a 1 over here, and then it becomes pretty difficult to figure out how to do a two-pointer approach because not all elements over here are even greater than the ones over here. And I guess that's actually true, even if I didn't have this one over here. But anyways, you get the idea. This is a little bit of the intuition of why this trivial two-pointer approach isn't super easy to reason about. But that actually does not mean that a two-pointer approach is not going to work. Actually, that's exactly the solution to this problem. It's going to be linear time and linear space. And this is a little bit of the intuition of it. And after I give you the intuition, I'm going to show you visually how it's going to work, and then we'll code it up. Suppose I try to put a pointer over here. This is my left pointer, and I'm saying that if this basically was my boundary, if I want to include this prefix, and I have my right pointer all the way here, what's the furthest I could shift my right pointer to the left to guarantee that all of these are, first of all, in non-decreasing order, and that all of these are greater than or equal to everything in my prefix over here? So let's say I do exactly that. I shift this pointer like that. I do all that, and now my pointer is over here, and I say that, okay, this is the boundary, not because this value is not greater than 1. It clearly is, but this is the point where the elements are no longer in non-decreasing order. And so this approach, I'll quickly just go through it. It seems like it'll work, and for this example, it actually will, because now we're going to shift the left pointer. We're going to try to find the middle array starting from here, and we will validate this part. We'll validate that it's in non-decreasing order. And so then this will be the boundary, and all of this like still looks good. So we'll keep shifting. We'll get here, and then this will be the boundary, and then this is the result. We will have found the result. We'll validate these are in non-decreasing order. All of them were less than or equal to this one. And eventually our left pointer is going to get over here. And that's the point where we see, okay, this one is no longer greater than or equal to this one. So we really can't do anything anymore. And so it kind of seems like this one worked, but actually it doesn't always work. If I change the example to something like this, I believe if I do this, now, by changing it to this example, something interesting is going to happen, and that's going to allow us to identify the optimal solution for finding the minimal middle array that we can remove. We'll try this again and pay attention to what we're doing. Don't just glance at it and not think about it further than that. Watch. So from here, I want to find from this point, what's the smallest middle array we could remove? Okay, so while my right pointer value is greater than this one, I'm going to keep shifting. And of course, while these are in non-decreasing order. So keep shifting, we'll get to here, and then we can't go further. So this is the case here. Okay, now we shift the left pointer to this spot, and this is where it's going to get interesting. Now my right pointer is over here. So I want to look at this point. The right pointer in this case is actually misleading right now. Even though this is non-decreasing, this value is actually smaller than this one. So we recognize that we had to shift the pointer to the left, but now we don't have to do that. We actually have to shift the pointer to the right. So now we shift the pointer over here, and now we're actually good. This value is greater than or equal to this one. So now this is the middle array that we would remove for this particular value. And so once again, shifting the left pointer, now I'm over here, right pointer is over here. We will end up shifting the right pointer once, and then this is the middle array we would remove. And for this example here, sorry I drew the box around this earlier. This, I believe, actually is the solution that we would remove. So the result in this case, I believe, would be 4. This way is what I'm actually going to code up first. And I think once you code it up this way, by doing 3 different pieces. So first I'm going to find what's the shortest prefix we could remove. Then I'm going to do the second, what's the shortest postfix we could remove. And then I'm going to do that algorithm I kind of just showed you up above, where we remove the smallest middle array. And among all of those, we'll try to minimize it. And that's what we'll do. If you notice, each of these pieces runs in linear time. We don't need any extra data structures, so it's going to be constant space. Let me just quickly show you how we're going to do each of these. Once I show you each of those, you'll probably see how I'm going to optimize this part. Specifically, what I'm going to do when I optimize the code, or not optimize, but shorten the code, I'm actually going to combine these 2 pieces. But I wanted to show all of them separately because I think that's very useful for beginners. But let's quickly just show how we're going to do the prefix. Counterintuitively, we're actually going to initialize the right pointer over here. And what we're going to do is find the longest stretch from here that is non-decreasing. We know that it's going to end over here. And so that tells us that that was the longest non-decreasing portion. So we would have to remove this prefix. That's the shortest possible prefix we could remove. Because if we try removing this, nope, the rest of the array is not in non-decreasing order. So that's how we're going to get the prefix. And if you notice that, look, the indexes are like this. And when my right pointer is over here, it's at index 5. And there's exactly 5 elements to the left of it. So that will actually tell us what is the length of that prefix. And then we'll do kind of similar for the postfix I already kind of talked about earlier, but we'll have a pointer over here, keep going while the values are in increasing order. Value will end here. So I want the length of all of this. So what I'm going to do, I believe this is index 5, 6, 7. I'm going to do the length, which is actually 8, minus 1 to get to over here, and then I'm going to minus the left pointer. And then we'll do the middle part as well. So we're going to do the first step, which is removing the prefix first. I'm going to just get the length of the array because we're going to need it so many times that we might as well do that. So that's the length, and we want to initialize r to the last position, which is n minus 1. And then while the values are in order. So at the array to the left of right pointer, we want to get the r minus 1. While that is in order with the current element, then we can shift the right pointer to that position safely. So we will decrement the right pointer. What if the right pointer reaches 0? Well, then we're going to get r minus 1. That could be an out of bounds error. So let's just make sure that r is actually greater than 0. Because if it's equal to 0, then that's basically telling us that all of the elements are already in order. After all of that's done, remember, we can initialize the result now to the r value. That will be the prefix. If r is at 0, then that means the prefix that we're removing is of length 0. So that's great. Now, next thing is remove the postfix. Let's try that, get the length of it. Pretty similar to up above, left equal to 0. And while the values are in order, the left value is in order with the one to the right of it, so L plus 1. While that's the case, increment the left pointer by 1. Well, let's make sure that left stays in bounds. So we want to say, let's say left plus 1. We don't want left plus 1 to go out of bounds. Don't want an index out of bounds error there. So let's say that is less than n. So there you go. Let's just think of the example once again. So if I had something like this, 1, 2, so my left pointer would go here, and actually then it would go to 10 because these two values are actually also in order. So my left pointer would end here, and it won't go any further because these are in decreasing order then. So it'll say this is the longest prefix we can keep. This is the shortest postfix that we could possibly remove, keeping the array valid. How do we get the length of that? It's going to be, I believe, n, which would be this position over here, minus 1, which will give us the last index, minus the left index. So we'll say n minus 1 minus left. We want to try to minimize the result, so let's do this. Result equal minimum of itself, as well as what we just computed right now. So we're done with the first two steps. Unfortunately, the third step is going to be the one that is the trickiest. You might notice some repetitive work in the third step that I'm about to do. Remove middle. So initialize left and right pointers to the ends of the array like that. And while the pointers have not met each other, the reason I'm not doing less than or equal is because this is what I'm going to be doing inside of this loop. So let's say I just have a very simple array 1, 2, 3 or something like that. If my left pointer is over here and my right pointer is over here, I want all the elements in between that. Because by definition, if I'm doing this, I'm removing a postfix. We already did that. And I don't want to remove a prefix either. We did that as well. So I only want to try removing things that are actually in the middle. Now, to calculate that, we're going to do this minus that, and then minus 1 again to remove like this part as well. So that'll give us everything in between. And if both of the pointers were at the same element, and we do r minus left minus 1, that's going to give us a negative value, and we definitely don't want that. So that's why I don't want the pointers to meet each other. So there you go. Now, inside of the loop, there's two possibilities. We want to shrink the valid window. It's going to be actually several conditions because there's a lot for us to do. So what I want to do inside of this loop is take my right pointer and shift it to the left, kind of what I was doing in the drawing explanation. We can only do that if two things are true. First of all, the portion has to be in non-decreasing order. So basically r minus 1 has to be less than or equal to the value here. And also we need the value in the left position to be less than or equal to the value in the right position. So we need both of these to be true. And by the way, a little bit of repeated work you can see up here. Who knows, maybe we didn't need to initialize the right pointer over there. Maybe we could have reused the right pointer that was here. Little hint for you. But anyways, for this part, this is looking good, but we do have to make sure, once again, that like the pointers don't meet each other. And I should get rid of this equal sign. Sorry, I was using that just to talk about it. But we want the left pointer to be less than the right pointer. And then we'll do this. The reason I'm actually going to do this as left plus 1, though, is because of how we're calculating the distance. Like down here, once we validated the window, the middle of the subarray, we're going to update the result like this, result, and then right minus left minus 1 for reasons I talked about. But if the left is less than right, and then we decrement the right again, then they could actually be equal, in which case this will yield us a -1 result. And that's why I'm saying left plus 1 is less than that. So I don't want the pointers to ever meet each other. They can only get to be adjacent to each other. I'm actually going to add one more condition here, which I'll mention a little bit later, but now you can kind of see why like this part is definitely the most complicated. But next is the part where potentially maybe we want to actually shift the right pointer to the right, in which case we want to expand an invalid window. The window is invalid. Instead of trying to optimize it and shrink it, we're actually just trying to make it valid if it's possible. We need the window to be valid. And the reason it would be invalid is if the value at the left position was actually greater than the value at the right position, in which case we would want to increment the right pointer. And now you can see why I'm going to add another condition, because what if the right pointer becomes out of bounds? Okay, so I need the right pointer to stay less than n, and then I can do this part if we're incrementing the right pointer. Well, still, we might, with this loop, have the right pointer reach out of bounds. It could reach out of bounds. We might get to a position like this, where I have 1 to a 10, and then I have like a 4 or something. If my left pointer was over here and my right pointer is over here, 4 is not good enough. It's too small. I have to shift my right pointer over here now. And basically at that point, we're removing a postfix. which is another reason why we're going to be combining these two pieces in a bit. But now you at least know the reason why. For this, we also need to add this condition up here because on some iteration of like this loop, this part might run. And then on the next iteration, we're going to run this part. We don't want to get the out of bounds error. I know this is like not super easy to understand. I know there's a lot going on here. I will show you the shorter code of this, but I think it's hard to just jump to that more concise solution without kind of going through these steps. There's only one thing here that we kind of missed. First is actually incrementing the left value, but remember that even the left value, the left portion has to be in non-decreasing order. We didn't really add that anywhere in this part. We added that over here. Since the value at the left index is actually non-inclusive though, we can't really just take this and add it here. If you don't believe me, try it on an example. So I'm just going to add that over here as an if statement. I'm going to say, if my left value is actually greater than the one at +1, just break out of the loop. So that, I believe, is the entire code. So now down here, I'm going to go ahead and return the result. I'll zoom out so you can see everything at once. Now, running it, you can see that this code works. It is efficient in the sense that it's like the most optimal time and space complexity, but we're going to now combine these two loops down here. We want this part to be remove a postfix or remove the middle. So consider the example, this one. My right pointer, by the time I finished the loop up above, was over here. Remember that. So right now, I initialized my left pointer over here. It's right there. And so I'm including this element. And I'm saying that as long as this value over here is greater than or equal to this one, instead of removing a postfix, I can actually be a little more greedy and remove everything in the middle. There's no need to shift this one further to the right. So that's what I'm going to do. So I'm actually going to remove the code over here and kind of update the loop that we have down here. I'm not going to update the right pointer. It doesn't need to be at the end of the array anymore. We can just keep the right value that we had after up above. And so now I'm going to keep this condition here. I want to validate before we do anything here that these values were in non-decreasing order. So now I'm going to update this part. There's actually no need to shrink the window anymore because, I mean, we definitely can't take the right pointer and shift it to the left. I mean, there's no way. We already determined that from the up above code. So now we can actually get rid of this part. It was pretty similar to what we had up above anyway. But we'll keep this part, actually. This part will stay the exact same. We might need to update an invalid window. And we will update the result the exact same way. And you can see that it'll actually work in both cases. So in the case where we're removing like a middle portion, it'll work. If the right pointer was all the way out of bounds, in which case like the right pointer is over here, that basically means we're removing a postfix. And the calculation does work if you take the right minus the left. That'll give you like this distance plus this part, and then you -1 for that. Like minusing 1 will bring the right here, and then minusing the left will give us the rest. So it works out. That's why we can keep this. And then this validation here, just to make sure that every time we increment left, well, they're actually in non-decreasing order. And so I think the rest of this is the same. Now you can actually reason about how a solution like this is possible. Running it, you can see now we are competing with the big boys. Now we got down from 3 loops down to 2 loops. And just so you know, I don't think like making this optimization really matters. If you had the previous solution, quite frankly, I think that one's more readable. I don't know if this was actually helpful. I think it's more helpful when I kind of optimize the code. If I had jumped right into this, I think it wouldn't have been easy to follow, but please let me know because maybe this video turned out too long for you guys. Maybe you guys thought looking at the longer code was actually more confusing. I'm not sure. But I think like for a lot of people, when they look at like the editorial and they see like a solution like this, they think, oh, wow, the problem must be easy. This is barely any code. It must be very easy. And then they try to understand the code and it's pretty, not easy to understand. Anyways, thanks for watching. Check out Leetcode.io if you like my teaching style and if you want to support me. I really appreciate it a lot, and see you soon.